It might even be a user mode thread related to an application like Notepad. And then that thread might come into kernel mode, and the same thing might happen to it. So it doesn't care where a thread's executing when it makes a scheduling decision. If you look at Linux time slices, you see something that's very similar. The time slice, the quantum, can vary between 10 and 200 milliseconds. The default is 100 milliseconds, so that's pretty close to what you see on Windows. But the difference is that the quantum of a thread, even a given thread, can vary across that entire range of 10 to 200. The way that happens is the quantum of a thread in Linux is tied to the priority of a thread. The higher the priority, meaning the more likely it is to be scheduled, the lower the quantum. Because it wants, if there's higher priority threads, it wants to give the low priority threads, when they get a chance to execute, a long time to execute, since the higher priority threads are likely to be running more frequently because they're going to be the ones chosen more. So if your priority goes up, your quantum gets smaller. If your priority goes down, your quantum gets longer on Linux. So again, if you look at the two, Windows is a kind of rigid system with just a few options, and Linux is a lot more fluid, trying to take into account how threads are using the CPU. In the multiprocessor support area, Windows, of course, is a multiprocessing OS. It supports up to 32-bit processors on 32-bit systems, up to 64 on 64-bit systems. Symmetric multiprocessing means that all the processors can access all of physical memory versus processors having their own private physical memory that's not accessible from another CPU. Also, all processors can take interrupts from hardware devices. It also supports non-uniform memory access systems, which is a variant on a symmetric multiprocessor. In a NUMA system, an individual processor has its own local physical memory, or group of processors might have their own local physical memory. Other processors can still access that physical memory that belongs to a different group of processors, but it takes longer to access remote memory than it does local memory. So it's still SMP, just differences in memory access, depending on where you're coming from. The scheduler has to be aware of NUMA systems, because what you don't want happening is having a thread that's executing on a particular node of the NUMA system, accessing its data in that physical memory, loading up that local physical memory with its own data, and then having the scheduler move it across the NUMA system to a different node. Now that thread, when it wants to access its data, has to go reaching across the system, something that you want to avoid. So the scheduler tries to keep threads on the nodes they're running on. The memory manager also is aware of NUMA systems, and when a thread allocates memory, it tries to give it physical memory from that node it's running on when possible. Windows also supports hyperthreading, what's called hyperthreading, or XMT processing, and that's where the processor actually is a single processor, but it appears to the system as two processors. Intel Pentium 4 Xeon systems come in this flavor. And the scheduler has to be aware of this kind of configuration, because if you have two physical processors that look like four system processors to the operating system, you can have a scenario where there's a thread busy on one of those physical processors, busy on the, let's say, logical processor 0. That second physical processor is totally idle, and so is that second logical processor of that first physical processor. Now, the scheduler, when it has another thread to execute, has a choice as to which of these three logical idle CPUs it can schedule that thing on. And what you don't want to have the scheduler do is to schedule it on that second logical processor of that physical one that's already busy, because then that thread's going to be competing with that other thread that's already running. You want the scheduler to put it on that second physical processor that's totally idle. So the scheduler has some smarts about hyperthreading built into it. Linux also supports SMP, whereas Windows has these upper limits built into it of number of CPUs it can support. And this, by support, I just mean run on. I don't mean use effectively necessarily. Linux has no upper limit. It's a compile time option, so you can go download Linux source code and compile it for however many processors you want. There's actually a version of the Itanium source tree for a particular SGI machine in the Linux source kernel, and the source is 2.6 kernel, most recent one, that's predefined to support to run on a 512 CPU system, even though no such system really exists. All CPUs can take interrupts. Supports non-uniform memory access. The place where it's different from Windows support for NUMA systems is that the memory manager hasn't been made aware of NUMA. The scheduler has, but the memory manager doesn't try to allocate memory from local nodes. It also supports hyperthreading, just like Windows does. If you look at virtual memory management, Windows, if you look at 32-bit Windows, splits the user mode address space, or splits the 32-bit address space into a portion that's going to be used by the operating system and a portion that's going to be used by app processes, user mode processes that run, like Notepad and Word and so on. And that split by default is right in half. 2 gigabytes of that 4 gigabyte address space are usable by the applications. 2 gigabytes are going to be used by the system, by the operating system and drivers. Here's a picture down here that shows that default split. And so what you've got are different user mode address spaces. Whenever a thread from a different process runs, Windows Memory Manager swaps whatever's mapped into this 2 gigabytes with the address space of the process that it's scheduling, like Notepad. It supports all the features that you'd expect out of a modern memory management subsystem, and all the features you'd expect and more, actually. It supports 32-bit or 64-bit, so there's a 64-bit version of Windows. It supports copy on write, so that applications can share memory, and then when they modify it, it becomes private to them, the modifications. It supports shared memory, so applications can share data easily. And it supports memory map files, which are used for image execution, for example, like running a program is mapped into the address space of the executable. On the Linux side, it also, in the 32-bit version, splits the address space between the system and user mode processes. The default split, though, instead of being 2 gigabytes like in Windows, is 1 gigabyte for the kernel, 3 gigabytes for user mode. You can actually move that line anywhere between those 2 points of having the operating system have 1 gigabyte anywhere to 3 gigabytes, with the remainder going to user mode processes. And I failed to mention that on Server 2003, you can also move that line anywhere between 2 gigabytes and 3 gigabytes on Windows. So that's very similar usage of those address spaces. Where things are different are that there's a version of Linux, Linux Red Hat Enterprise Edition, version 3, that supports a different split. It's called the 4.4 option, or 4.4 split, where the user mode processes all have an entire 4 gigabyte address space, and the system process all has an entire 4 gigabyte address space. So they've got a lot more memory, a lot of more virtual memory to play with, which is good for memory-intensive applications like database servers or web servers. Where you get a disadvantage with that approach is that anytime the user mode process wants to call in a service from the kernel, this memory manager has to switch the address spaces, something that's an expensive operation. So 4.4 split, as long as the application doesn't make many trips into the kernel, is a performance advantage. Otherwise, you're going to be paying a heavy price for it. Linus is resistant to put that into the mainstream kernel, by the way. That's a Red Hat specific enhancement. The Linux Memory Manager supports all the things you'd expect, just like a Windows Memory Manager of 32-bit or 64-bit, copy and write, shared memory, and memory map files. So that's the way that Windows and Linux manage the virtual memory of the processes running on the machine. Let's talk about how they manage the physical memory. So physical memory management means you've got a fixed amount of physical memory. What processes do you let use that physical memory? Your goal is to give physical memory to the processes that need it the most, the ones that are most memory hungry and actively using their memory. Processes that aren't using physical memory or that are idle, you want to take memory away from those guys and give it to the guys that need it. What you do with the pages you've taken away, the data that was stored there, is send it off to the paging file and then bring it back when you need it, when that application wants to access it again. One of the policies that a memory manager designer has to decide on is when a process needs another piece of memory, another page of memory, where that page of memory should come from, where that physical piece of memory should come from, who should steal it from if all the physical memory is in use. Windows has what's called a per process working sets, where a working set is the list of physical memory assigned to that process. And the page replacement algorithm, the algorithm the memory manager uses to decide who to steal a piece of physical memory from to give it to a process needing another page, is called local page replacement. And so here's a picture of local page replacement. This process here wants another page of physical memory. And what the memory manager does when it decides this process has gotten big enough and there's no more free memory on the system, it's organized the memory that that process is accessed from most recent to least recent. And it will take the least recently accessed, the one that the memory that the process has accessed most distantly in the past, figuring it's not going to need it again in the near future, and steals that page away from that process, giving it back to it to use for whatever it wants to use new memory for. Now, the other processes also have their working sets on these lists that are sorted that way. But Windows will steal from the process that wants the new memory. That's in contrast to Linux memory management, where it uses a global working set algorithm, where it also sorts the list of pages of physical memory on the same least recently to most recently accessed